the solubility product constant describes how much of the compound can dissolve. It does this by being an equilibrium constant, allowing us to know the concentrations of the compound dissolved in terms of moles per liter. The molar solubility of the compound, which we'll represent with S, which is very similar to X that you had done in previous ice tables. Now this molar solubility, the number of moles per liter that you could dissolve, the molarity, this can allow you to find the solubility of the compound in terms of grams per liter. Solubility of the compound is defined as grams per liter, whereas molar solubility is moles per liter. And also the molar solubility allows you to find the concentration of each ion, the number of moles per liter of each ion instead of the entire compound. So we can go from left to right or from right to left, either way in this. Okay, so in our first problem, say that we have the solubility of silver 1-phosphate, which is 0.0067 grams per liter. So this is the maximum amount you can dissolve at equilibrium, aka this is the solubility in a saturated solution. Now, being in a saturated solution, wow, fail. Being that it's in a saturated solution, you know that Q is equal to KSP. You know that the concentrations of each of your ions dissolved is related to the equilibrium constant, and therefore you can now find the KSP. So we can go from the number of grams per liter of silver phosphate dissolved into the number of moles per liter, the molar solubility. And from that, we can get into the solubility product constant, or the equilibrium constant for this dissolving. So again, there's only a relationship between the molar solubility of your compound and KSP, the equilibrium constant, if this arrangement is in equilibrium, aka it's in a saturated solution. So being in a saturated solution, we're in equilibrium. There is a relationship between the current amounts dissolved and the equilibrium product constant. Okay, so being in our number of grams per liter, we can go into our moles per liter. Just convert from grams into moles using molar mass. So we now know that the molar solubility is 1.60 times 10 to the negative 5 moles of silver phosphate per liter. Now, having this molar solubility S, we're able to find KSP. We can see that this reaction allows us an ice table where we have initially just some solids, so we can ignore everything in the change of that silver phosphate. And we'll get 3 times as many moles of silver dissolved as moles of phosphate dissolved. So for every 1 mole of silver phosphate that dissolves, there's 3 moles of silver and 1 mole of phosphate. So we can plug in this S, which is just like the X that you've seen, into our equilibrium expression. And so doing this and accounting, importantly, for the coefficients, we are able to find that the KSP is equal to 27 S to the 4th power for this silver phosphate. And so plugging in then the value of S, our molar solubility, we can find the solubility product constant, KSP, 1.77 times 10 to the negative 18. You'll note that this is a very, very small number. This small number means that the solubility of silver phosphate is quite low. So the higher KSP, the higher the solubility. Okay, let's try another one. This time, let's go from KSP into the solubility. So essentially, the reverse of the problem that we had just done. So we have KSP. In order to get into the solubility in grams per liter, we need to find the value of S. So KSP and S are related by the equilibrium expression. So if we know KSP, we can find the value of S by having values built from our ice table. And so our ice table allows for 1 mole of barium produced for every 2 moles of fluoride produced and dissolved. And we'll again account for this coefficient. This 2 is coming from the 2 in front of the fluoride here. And so we can find the value of S, which is in moles per liter, and then to convert into grams per liter, we just need to use molar mass, 1.32 grams of barium fluoride per liter. Thanks for watching, guys.